Okay, so we're going to do a little bit more complex example of conservation of energy. So our problem is going to be this. Tarzan drops from a 20-meter high branch in a tree holding onto a 30-meter long vine, which is connected to a second tree. So our first step is going to be to draw a picture. Let's go ahead and do that first. So he's in a 20-meter tall tree. So let's say here's our tree. Here he is standing 20 meters up, and he's holding onto a branch that is, branch or vine that is 30 meters long. So we need to make sure, kind of draw it in proportion. It's got to be a little bit longer than this. So there we go, which is connected to a second tree. So here's our second tree. It's connected to some branch. So when he swings down on the vine, you're going to notice that this length right here is going to stay the same. So I'm just going to use a ruler to measure out how long that is, just so I can keep it consistent, so the picture kind of looks right. It's about 3 centimeters long, which means at the very bottom it's going to be about 3 centimeters long also. So we know that this is also 30 centimeters, or 30 meters, sorry. And it's going to make a path that looks something like this, where he's going to stop on this tree. We'll call this his H max. It's maximum height he reaches. Okay, so now we need to know, let's just talk a little bit about this picture actually. What kind of energy does he have in certain spots? So he has total potential energy up here, potential energy, gravitational, and he has total kinetic energy down here. Okay, so when we are asked if he barely skims the ground, so that'll be right here, at the bottom of the swing, how fast will he be traveling at the bottom? So this is our initial position, and this will be our final position. So we always want to start out our equations looking something like this. Energy initial equals energy final. And in this case, the only kind of energy initial that he has is potential energy gravitational. The only kind of energy he has at the end point is kinetic energy. So let's go ahead and write our equations. mgh equals 1/2 mv squared. Well, you can see that mass doesn't really matter because it's in both factors, which is why I never gave you mass, so we can cancel that. We're left with gh equals 1/2 v squared. We want to know the velocity, so in order to solve for that, we want to multiply 2 on both sides. That cancels out our half. Multiply 2 on the other side. So we're left with 2gh equals v squared. We want to know velocity, so let's take the square root of both sides. We're left with v equals the square root of 2gh. We can plug in our knowns. We know that gravity is 9.8. We know that the height that he starts at is 20 meters high. When you plug that in your calculator, you should get .79. So round up, you get 19.8 meters per second. Great. Let's move on to C. What is his maximum height that he will swing up to on the other side? So we want to figure out what is this H max. Well, we know down here at the beginning he has potential energy gravitational, and at the very end he's going to convert that energy back into potential energy gravitational. So our equation is energy initial equals energy final. He has potential energy gravitational at the beginning, and he has potential energy gravitational at the end. mgh is equal to mgh. Once again, our m's will cancel. Gravity is 9.8 on both sides, that cancels. So you'll notice that this 20 meters on the left-hand side must be the H max on the right-hand side. Okay, so let's do part D. Repeat B and C, assuming he pushes off with a velocity of 10 meters per second. So now we are actually adding kinetic energy at the initial point because he has a speed. So now he'll have an energy initials, potential energy, gravitational, plus kinetic. Then at the final point, for part, we're repeating part B right now. So he's only going to have kinetic energy at the end. So energy initial equals energy final. Potential energy gravitational plus KE equals KE at the end, right here. So let's write our equation. mgh plus 1/2 mv squared equals 1/2 mv squared. And this is our initial velocity, and this is our final velocity. You'll notice there's a common factor in all of those, m's, so they cancel. And we want v final, so you should get comfortable with go ahead and solving before you plug in numbers. So let's do that. GH equals 1/2 v initial squared equals 1/2 v final squared. And if we multiply the whole thing by 2 to get rid of these halves, let's multiply everything on the right hand side, everything on the left hand side by 2. You'll get rid of this half and this half, but we're going to be left with a 2GH. So 2GH plus V initial squared equals V final squared. Okay, so let's solve for VF. VF is equal to the square root of 2GH plus V initial squared. Let's plug in our givens. Gravity is 9.8, height is 20, and his V initial was 10 meters per second. When you plug all that in your calculator, you should get 22.18 meters per second. So let's round that up to 22.2 meters per second. So that is his velocity now at this point at the bottom. You can see that given an initial velocity in this second scenario, he has a greater velocity at the bottom, which makes sense. Because he has more energy at the top now, he must have more energy at the bottom also. So let's go ahead and solve for C again, considering that he has an initial velocity. So this is our repeat C. So our energy initial is equal to energy final. And we are going to have, at the beginning now, our initial position is going to be here, and our final position is going to be up here. So we have potential energy gravitational plus kinetic energy equals potential energy gravitational at the end. So mgh initial plus 1/2 mv initial squared equals mgh final. And we want to know the final height. So if we go ahead and cross out anything that we can, m's are common in everything. And let's divide through by gravity to get h by itself. We're left with h initial plus m's canceled. So v initial squared over 2 times gravity, because we have to divide by g, equals h final. So h final is equal to, our height initial was 20, and our v initial was 10. So 10 squared divided by 2 times 9.8, and we get we should get 25.1 meters. Make sure you're actually putting this in your calculator yourself, so if you have to ever pause the video to try these out, I highly encourage it to make sure you're able to do this on your own. And last but not least, part E, we need to know what is the angle, what angle does the vine make with the vertical. So if we go back up here, what angle does the vine make with the vertical? You'll notice in the picture that, well, I should have extended this a little bit longer. That's our 30-meter rope. And then it goes, makes a right triangle here. You'll notice that this part is 20 meters high. So that means if this part is 20 meters high also, that must mean this section is 10 meters. Obviously you can see mine isn't proportional. So 10 meters on this side, and we know the length of the rope is 30. So let's go ahead and draw that triangle. So here's our vine, it's 30. We noticed that this part was 10. And we want to know this theta that it makes with the vertical. So we can use our trig functions to notice that this is the adjacent side, this is the hypotenuse, so cosine theta equals 10 over 30. And we want to find theta, so let's take inverse cosine of 10 over 30. Make sure your calculator's in degrees. And you should get 70.5 degrees. And since they already identified that they're asking for the angle with the vertical, we don't need to include a direction because there is only one angle with the vertical. Okay, this angle is not with the vertical, that's with the horizontal. Okay?